Alright, so today I was assigned...
Make sure that shoulder doesn't come in too far.
Problem number 13, which is the square problem, almost a replica of number 12, just different charges. There's some negative charges, so we're going to have some opposite negative charges and some opposite positive charges. So let's place them here like that. Uh, 6 millicoulombs and -6 millicoulombs, sorry. Then 6 millicoulombs, -6 millicoulombs, and 6 millicoulombs. And it's a square, so each is going to be 0.1 meters across. That value will not change. And so, we are going to have these two positive, the positive and negative charges are going to be attracted to each other, and they're the same, so the value of the 6 isn't really going to matter in this case. So we're going to have a vector going this way and this way. And then this positive acting on this positive is going to result in a positive vector going that way. So we're going to have a vector diagram kind of like this. So I'm going to focus on this charge here. If I didn't clarify that earlier, I'm going to use Coulomb's law to find the charges on this from these negative charges. So Coulomb's law, K times Q1, Q2, all over R squared, so we're going to get 9 times 10 to the 9th times 6 times 10 to the -3, or 6 times 10 to the -3, it's a millicoulomb, I'm sorry, excuse me, all over 0.1 squared is the radius. If you didn't already notice, these are the same, so this is going to be squared. Okay, so do the calculations for this, and you get 3.2 times 10 to the 7th newtons. That's going this way, and that's going this way. I'm not going to worry about signs yet, because I'm going to let my vectors do the work. So I'm going to redraw my diagram. So we have a 3.2 times 10 to the 7th, and 3.2 times 10 to the 7th. But we also have to worry about this vector here. It's going in an opposite direction. And we're looking for the total magnitude going this direction. Are going to be the same because it's a square. And so what we are going to do is now focus on this vector. So I'm going to use Coulomb's law again, but this time I'm going to do, we have to use the hypotenuse as the length, because it is a 45-degree triangle. This is 0.1. This is also 0.1. This is going to be 0.1 root 2 if you remember your laws. So I'm going to use Coulomb's law again. Let me just set that up. 9 times 10 to the 9th times 6 times 10 to the -3 squared all over 0.1 root 2 squared. Do all the math for this, and you get 4, and no, I'm sorry, you get 1.6 times 10 to the 7th. Vector resulting that way. So, you have vectors going in different directions. We aren't worrying about the signs because our vectors are doing the job for us. We are going to do some vector addition. So I have 3.2 times 10 to the 7th. To add those vectors, because they're going in supplemental directions, oh, sorry, we're going to do simple vector addition, 3.2 times 10 to the 7th squared plus 3.2 times 10 to the 7th squared is equal to c squared. So you're going to find the square root of c. This is going to give you an answer of 4.5 times 10 to the 7th is the sum of those vectors. However, you also have this vector going this way, so you're going to want to subtract this 1 point. Let me redraw that so you know what I'm referring to. You're going to want to subtract this 1.6 times 10 to the 7th. So we're going to get 4.5 times 10 to the 7th newtons minus 1.6 times 10 to the 7th newtons. And the final answer, these are going to give you 2.9 times 10 to the 7th newtons, all towards the center. This is the magnitude. That's all I got for you guys.
Nice, dude.